And welcome back. Folks at home can hear me, yes? Thumbs up-ish, good. All right, we are live and ready to go. All right, so last time we were talking about Homo and Lumo in pi systems. And I just wanted to clarify, some of you have been a little bit concerned about whether or not I'm going to ask you to generate those extended pi orbitals from scratch or not. And the answer is, I'm not. I showed you where they came from because I wanted you to understand their interesting shapes. Last time we were dealing with this allyl anion, and as you recall, we had drawn different pi orbitals, and I guess we can fill in the colors. We had identified the nodes, ranked them in energy, and finally chosen Homo and Lumo. I showed you these orbitals where they came from, because I sort of wanted you to know why there was a node that coincided with carbon 2. But the place where I wanted you to be able to get on your own eventually was to be able to look at a resonance structure of a molecule that has a system of pi orbitals, and to identify what the Homo and Lumo are if I give you those pi orbitals. So as an example, not sure I intended to do this, but I'm gonna. So this may have been a test question in previous years. This molecule has lots of resonance structures available to it. One of them puts the positive charge on atom 3. Another one of them would put the positive charge on atom 1. And now I will draw for you the pi orbitals of this molecule. Going to take me a minute, so I apologize. It's going to take me longer because I don't like my drawing. There's one. There's another one. Let's see, there's another one, and another one, and another one, and now all I got to do is fill in the phases. I like to color both lobes, but since I'm not wanting to bore you any more than I usually do, I think I probably will just fill in the one. All right. So those are 5 pi orbitals available to that carbocation, which is Homo and which is Lumo. So what do? How do you rank pi orbitals in energy?
Vertical nodes.
Vertical nodes. Remember the slinky, right? So I just have to identify every place where the phase switches. All of these orbitals have a horizontal node in the plane of the carbon atoms. We're not going to really worry about that because that's not a difference between them. So this orbital doesn't have any vertical nodes. This one looks like it has the maximum number of vertical nodes. The one to our right looks like it has 2, and then another that corresponds and coincides with carbon 3, so that there's no electron density on carbon 3 in that orbital. This one has just 1 node, but it also coincides with carbon 3. And then this one has 2 nodes, and they correspond to carbons 4 and, well, sorry, I guess I'm getting mixed up as to who's what. Carbon 2 and carbon 4. Does that make sense so far? To see where we're getting the nodes from? All right. So in some ways, it's just can you watch the places where the wave function switches sign? Can you count those? And can you remember that the more nodes the orbital has, the higher in energy it is? So let's rank them now. Which should be my lowest? Top left, the one with 0 nodes. So maybe we'll call that pi 1. All right, who's next? Remember how I told you that if you could count, you could do most of the math in this class? This is one of those. This is one of those times. Okay, so we'll just continue with an increasing number of nodes. Pi 3. This would be the 4th one, and then this one would be the 5th. Okay. All right, so now we know their relative energy levels. One interesting thing to notice, and again, this would only matter if I was going to ask you to generate these orbitals from scratch, which I'm not, but they follow an interesting pattern. Do you remember that symmetry rule that was confusing about MO theory? The orbitals needed to be either symmetric or anti-symmetric relative to the molecule. There's sort of this alternating pattern where you have the lowest energy one is symmetric, the next one is anti-symmetric, then symmetric, then anti-symmetric, then symmetric, and it alternates in that pattern. And that's a pattern actually generally for pi orbitals. It may or may not be useful to you, but needing to fulfill that pattern is one of the reasons why we have the nodes where they are. Any other combinations would violate that symmetry rule. So that's just a dumb little aside. Oh, and before I get any further, let's see, we got a TA monitoring the chat. Yes, Wallace is monitoring the chat. Very good. All right, so, and Wallace, feel free to unmute. No, you're right there. So feel free to chime in anytime there's a question that a lot of people are asking or that we need to deal with.
Quite a few people are asking how you know about the nodes that are on top of the orbitals and how you know where those go.
How you know about the nodes that are on carbons?
Yeah.
Okay. Yeah. So there's a few answers in all of them unsatisfying, I'm sure. So the first answer is the most unsatisfying one, which is because the math makes it that way. You do the math and you calculate how much of the orbital is on each of those atoms. And for pi 3, the math tells you there is 0 orbital on carbon 2 and there is 0 orbital on carbon 4. Okay, so that's not that satisfying because it's this mysterious box of math that says that things have to be the way they are. The other way that you know that they have to be there is if you remember this symmetry requirement. If you remember that the orbitals need to increase 1 node for each of our 5 pi orbitals, so you know that, for example, ahead of time that pi 2 is going to have 1 node, and you also know, according to the symmetry rule, that it needs to be anti-symmetric, what we've drawn for you there is the only way you could put 1 node in an orbital that spans 5 atoms and still have it be anti-symmetric. And in fact, it's sort of an even versus odd thing. If you are doing a pi system with an even number of atoms, like 1,3-butadiene, that has 4 pi orbitals, and they have nodes, but none of them are on atoms that are, none of them are on the atoms. And it's a symmetry thing. When you have an even number of, when you have an even number of orbitals, an even number of atoms in the pi system, there's no need for a node to correspond to 1 atom's position. When you have an odd number of atoms, some of the nodes are going to have to coincide with the atoms just to obey the symmetry rule. And then the final answer is that if you draw up all the possibilities for all the unique possibilities for putting one node in a list of 5 on over 5 atoms, and you add them all together, you come up with that answer. So, all right. Now, in terms of assigning Homo, go ahead.
So maybe I should already know this, but you're going to have the same number of pi configurations as you do carbon atoms, right?
Yes, you're going to have the same number of pi orbitals as you have carbon atoms in the pi system, carbon atoms participating in resonance, because each one contributes 1 p orbital to that system of molecular orbitals. Yeah?
So if there was a triple bond in the middle of this molecule somewhere, this would probably no longer apply.
If there was a triple bond there, well, it depends. If the triple bond were conjugated with the other double bonds, it would be just fine.
Okay.
But the other pi bond in that triple bond wouldn't be part of it,
Okay.
because it'd be held 90 degrees away. Yeah. Okay. Yes?
How would this, if it was a benzene ring?
Yeah.
Resonance, how would that look? Would there be an exception?
Oh, wow, that's a fantastic question. And you will find that you can probably derail me off onto chemistry tangents and limit the amount of stuff I'm able to teach you if you ask great questions like that. So strategy to win in the course. What do you do in benzene? Well, in that case, you don't have a line of orbitals now, you have a ring of orbitals. And that creates a unique situation where you get extra stability because you have a ring of orbitals that encircle the molecule, and you've got the possibility for electrons to be delocalized all the way around instead of just in a line. And in chapter 16, which is in 352, you will learn about the special stability that you get from that. It's called aromaticity, and it's really kind of cool, but I'm going to punt until then. All right? Okay. Good. So, if we want to assign Homo versus Lumo, what do we got to do? Well, we got to count the electrons that are part of the pi system and then fill up the orbitals from lowest to highest. And to figure out how many electrons are in the pi system, you simply count the electrons that are in double bonds or lone pairs that are involved in resonance with those double bonds. So in this case, we've got 2, 4, and that's it. We've got a positive formal charge on the carbon, so we know there's no lone pair there. 2, 4, and then Homo and Lumo becomes easy. Right? You can get tripped up on these questions if you count the electrons wrong. So for example, if I changed this problem and put a negative charge there, you would need to realize that I've got 2 extra pi electrons, so now the Homo would be pi 3 instead of pi 2. Yeah, go ahead.
Can you do that one more time, just really, really slow?
Really? Okay, which part?
So I'm looking at the whole thing, I see that there are 5 carbons there, and I would say that there are 20 electrons because of that.
Okay.
Minus 1 for that.
Okay, so you're counting all the electrons in the molecule.
Yeah.
The ones that are in the sigma bonds, 2, 4, 6, 8, 10, 12. Am I missing any? Oh, and then all the other hydrogens. Okay. Just for clarity's sake, I'm going to draw the hydrogens that are implied but not shown. All right, we've got 1, 2, 3, 4, 5, 6, 7 carbon-hydrogen bonds. So that's 14 electrons in CH bonds. We have sigma bonds. We have, let's see, 1, 2, 3, 4 carbon-carbon sigma bonds. So we have 8 electrons in the carbon-carbon sigma bonds. And then I have 4 electrons in carbon-carbon pi bonds. it turns out and then there's none on carbon 5 because of the positive charge. We only count the electrons that are involved in pi bonds, and not just any pi bonds, but they're pi bonds that are part of this string of pi orbitals that are adjacent to each other, string of pi bonds that are adjacent to each other. The reason we only count those is because the reason we can ignore the sigma bonds is because this molecule is planar. You can imagine this molecule is flat in the plane of the page, and each of these carbons is trigonal planar. Each then contributes a p orbital to the pi system, and those p orbitals are above and below the plane of the page. So the purple lobe is coming out at you. And because it's above and below, and because there's these p orbitals have a node in the plane of the carbon atoms, we can ignore the sigma electrons entirely because they're not going to they're not going to interact with or participate in the p orbitals or the pi orbitals. Yeah.
Would all of this hold true if there's another pi bond involved with another molecule, like CO pi bond?
In another molecule, if you had a CO pi bond, what would that do? Fascinating question. What it would do, if you changed this one to oxygen, the orbitals would look basically the same, except the bonding orbitals would be leaning more towards the oxygen, and the empty orbitals would be leaning more away from the oxygen. That's not something you'd need to predict. But yeah, you can. That's one of the great things about MO theory. As long as you're putting in an atom that has the same alphabet of atomic orbitals, the MOs stay qualitatively the same. Yeah.
So the electrons in the pi bonds have to do with the double bonds.
That's right. Yeah. Yes.
If you had something like a structure like this that has resonance attached to like a benzene ring, would you count that as two separate pi
Systems?
systems?
Yeah, the question is, if I had something like this attached to a benzene ring, would I count it as two separate pi systems? The more you put in a chain, the harder it gets to answer that question. A pi system only works when the atoms are all lined up linearly, and the carbons are all in the same plane. The more you put in a row, the more entropy the chain has, and the more you're going to get twisting that sort of limits how long the pi system is. But yes, you can make quite long molecules that that are conjugated. And that actually has to do with vision, so we will talk about that in just a sec. What else? Yeah.
So if you had a lone pair, it would have to be adjacent to the
Right, if you had a lone pair, it would have to be adjacent to the series of pi bonds in order to participate. In other words, yes, that lone pair counts. No, that one doesn't. Yeah. Okay. All right, so in terms of your abilities, you need to be able to find the nodes, order the orbitals and energy, and count the right number of pi electrons. And then the problem's pretty easy. It's worth some practice, and I believe the practice exam will give you some chances to do that. One interesting thing we haven't mentioned is the energy difference between HOMO and LUMO, this delta E, is the energy of a photon that would be required to promote an electron from HOMO to LUMO. And one observation is that the more atoms you connect in an extended pi system, the smaller this gap between HOMO and LUMO gets. It's like you're trying to cram more orbitals into the same space, energy space. And so the spacing between the orbitals starts to get closer. For 1,3-butadiene, the difference between Homo and Lumo is such that it's an ultraviolet light that causes this transition. Incidentally, many of the molecules that we use as sunscreens have Homo-Lumo gaps that are tuned to absorb photons of UV light. But if you make molecules that have more and more pi bonds adjacent to each other or conjugated with each other, you can get Homo-Lumo gaps that are now in the visible light range. So the colorful clothing we wear has dye molecules in it where the Homo-Lumo gap is small enough that visible light can be absorbed. And this is also how you perceive vision. So let's see. And by vision, I don't mean the Avenger. Dun, dun, dun. Nobody laughs. It's okay. It's okay. I'm not offended. Not offended.
So the larger the pi system, the lower delta E is?
Yes. I'm trying to, no, is it not in here? I thought it was. Used to be in here, maybe isn't anymore. I'm going to need to look up a structure. So, let's see. I'm going to look up the molecule 11 Cis Retinol. All right, so in the back of your eyes, in your retina, you have some rod and cone cells. And in those rod and cone cells, in the membranes of those rod and cone cells, you have a protein, a membrane protein called rhodopsin. And inside that protein called rhodopsin, you have a molecule called 11 Cis Retinol, which I am drawing, and I haven't memorized it.
Professor, you don't have the drawing on.
I know, I'm sorry.
Just checking.
That's its structure. Yeah, sorry about that. Are we back so everybody can see the screen? Oh, but now I can't see what I'm supposed to be drawing. So just give me a second to draw it, and then we'll... Sorry. Dun, dun, dun. All right. I got methyl groups in the right places. Yeah, basically. Okay, sorry I don't have that memorized, and I should have prepared more. This molecule is called 11 Cis Retinol. Retinol would be when you just have the alcohol here instead of the aldehyde. It is attached to your rhodopsin protein in your rod and cone cells via a covalent bond. And notice here you have 1, 2, 3, 4, 5, 6 pi bonds in resonance or conjugation with each other. That's 12 carbon atoms, 12 pi orbitals. Homo-Lumo gap is just so that you can now absorb light. What actually happens here is, and we'll learn about this later on in the course, you've got this cis double bond here, and you have hydrogens bumping into each other. Hydrogens on this methyl group bumping into that hydrogen, and there's steric strain. That means that the molecule has to distort itself to accommodate all of that space. When you absorb a photon of light in this molecule, you promote it to a higher energy level, and that causes, that weakens these pi bonds enough that the molecule can actually rotate and relax to be trans. If the double bond was trans, we would take all of this and shoot. Can I do this fast? I cannot. I may have made some mistakes there in drawing it. quickly. I apologize if I have. But what this does is it causes the molecule to relax and change its shape. And that does something to the structure of the protein that opens an ion channel that creates a signal that gets transmitted to the optic nerve and interpreted in your brain. Now, it just took us like 5 whole minutes to talk about that, but that was going on continuously all the time while you were sitting there. You've had Homo Lumo going on inside your eyes since you were born, right? Yeah, so one of my goals in this class, in addition to teach you things that you think you have to memorize in order to pass standardized exams in your future, is to show you that you can understand things about the world around you at the molecular level, and also to help you get to these aha moments where you see something sort of beautiful about God's creation that you can now understand. So, perhaps someday when you were gazing into the eyes of a significant other, you can compliment them on all of the Homo Lumo transitions that are going on in their retina. I don't know. Try that one. See how well it works. Go ahead.
So this is photoisomerization. So this is the runoff and bleaching.
Yeah.
Which sends the signal. And then in order for us to keep doing this, the system's continuously going bleaching and bleaching, bleaching and bleaching.
Right. So that's a good question. Once this isomerization happens, it turns out that protein is done, and it has to be transmitted to it has to be translocated to the retinal pigment epithelial cells, where they pull out the transretinal and put back in cis retinal, and then that goes back down. And so I don't really understand the whole process, but I think in vision, the rod and cone cells are continuously sloughing off these little discs of membrane that are full of rhodopsin, and it's because they got to recycle out. And so, yeah, it's awesome. I mean, it's more complicated than we said, because not only is the Homo Lumo stuff going on, but it goes on once, and then that protein's dead and needs to be recycled, and you are able to keep up with it fast enough that there's no flickers, at least, in your in your vision. So kind of cool. All right. Well, we need to develop some skills to be able to identify Homo and Lumo in organic molecules other than just those with pi systems. And because most of organic chemistry is going to involve the Homo of one molecule attacking the Lumo of another molecule. So I'm going to import a set of slides from that I made earlier based on MO theory calculations that give some examples of Homo attacking Lumo. And what I'm going to show you will make more sense if you've looked at the study guide already, but even if not, it'll be informative. Sure, fine. Yes. I'm trying to get them to teach this in detail in general chemistry because it's really cool. But we're going to see in organic chemistry, most of our reactions are going to involve the Homo of an electron-rich molecule attacking the Lumo of an electron-poor molecule. So I will just tell you, you don't need to know how to figure out that this was the case. We'll learn some of that in a little bit. That methanol is an electron-rich molecule, whereas BH3, borane, is an electron-poor molecule. So I'm going to be, for electron-rich molecules, we're going to be looking for what the Homo is. For electron-poor molecules, we're going to be looking for what the Lumo is. Just a few terms that might be useful to you are electron-rich molecule. We're often going to call a nucleophile because it's got electrons that it wants to share with a nucleus of some kind. We will also call it a Lewis base. In contrast, the electron-poor molecule, we will call it an electrophile because it is electron-poor and it wants electrons, loves electrons, or we'll call it a Lewis acid. For Lewis acids, we're going to be worried about the Lumo. For Lewis bases or nucleophiles, we're going to be worried about the Homo. Now, My goal for you is once you've completed the study guide, you should be able to look at methanol and say, oh, sure, the HOMO is the non-bonding lone pairs on that oxygen. And we'll talk through that in a minute. I also would like you to be able to look at borane and say, oh, yeah, the LUMO is the empty p orbital on boron. But even if you're not there yet, this is still instructive. These are the results of molecular orbital theory calculations in a program called Gaussian, which takes care of all of the math. And we have a wonderful supercomputer here on campus that can crank away at this stuff really fast while you go get a soda from the vending machine and check Twitter or whatever the kids are checking nowadays. I don't know. Guess who's not? I'm sorry. I got political. Guess who's not checking Twitter? He got what he deserved. Perhaps not all of what he deserved, but he did get what he deserved. Anyway, the calculations show you that the HOMO of methanol is a lone pair on the oxygen. It so happens that the calculations tell you that this lone pair actually looks kind of like a p orbital. That's okay. You can think of oxygen as you can still think of oxygen in water and methanol as being roughly sp3 hybridized. But this is what the HOMO looks like, and it is lone pairs on the oxygen. The LUMO of BH3, the calculation says, looks like a p orbital on trigonal planar BH3. Relative energy levels are given here, and I actually made this to scale. So the y-axis space here is sort of energetically to scale with these numbers. The units are weird things called Hartrees, which you don't need to worry about. In any case, if we mix the HOMO of our nucleophile together with the LUMO, we get a new bond. And the new bond we get looks exactly like you would expect if we took the blue lobe on methanol and overlapped it with the blue lobe on the empty p orbital on boron to make a new sigma bond. And that sigma bond looks exactly like we would expect just from overlapping a p orbital on one atom with an sp orbital on the other atom in phase. So hopefully this demonstrates we're not just making stuff up. This is what the math actually tells us. The new orbital that we make is lower in energy than the starting orbitals we make because the electrons are now shared between two atoms. Not shown here, of course, is the high energy antibonding orbital that would also be made by mixing these two together. So this is an example of a simple chemistry reaction that if you knew ahead of time what the HOMO and LUMO were, you could have predicted what would happen. All right. So motivated by that, and there's lots of other situations where HOMO attacks LUMO, let's first try to develop our intuition to be able to identify HOMO and LUMO in organic molecules. This is probably best done through a series of examples. The study guide has some detailed rules for walking through it, but it may be better to just try some molecules out and see where we go from there. So I'll take one from your study guide. Until you get good at this, it may help you to draw in the hydrogens that are not usually shown in our skeletal structures but are implied. All right. So there's two ways to identify HOMO and LUMO. There's the longhand way and then there's the shortcut way. The longhand way is to count all of the bonds in the molecule, identify which are sigma bonds and which are pi bonds, and then draw an MO energy diagram that accounts for all of the orbitals that you have present and fill them up with the available electrons. For example, I would say here I've got 4 carbon-hydrogen sigma bonds. So that means I'm going to need 4 carbon-hydrogen sigma bonding orbitals and 4 carbon-hydrogen sigma star bonding orbitals, or anti-bonding orbitals rather. Does that make sense? We've concluded every bond has to have a bond and an antibond, a bonding and antibonding orbital. Let's see, how many carbon-carbon bonds do I have? I have 1 carbon-carbon sigma bond. So that means I need 1 carbon-carbon sigma bonding orbital and 1 carbon-carbon sigma star. Then let's see, I have a carbon-oxygen sigma bond. So I'm going to need a carbon-oxygen sigma star and a sigma orbital and a carbon-oxygen sigma star. I have 1 carbon-oxygen pi bond, which means I should have a carbon-oxygen pi orbital and a carbon-oxygen pi star. And then lastly, I've got lone pair electrons on the oxygen. So I have 2 lone pair electrons. That means I've got 2 non-bonding atomic orbitals that I need to account for. Okay. With that list in mind, we can now come up with an energy diagram. And a challenge here is to know what are the relative energy levels of carbon-hydrogen, carbon-carbon, and carbon-oxygen sigma bonds. The answer is you could do the calculations and find out. You could look up bond strengths and get an idea of which bonds are stronger. But for our purposes, these sigma bonds are almost never going to be the HOMO, so it's really not going to matter which one is higher than the other when they're all going to be lower in energy than the HOMO. So for our purposes, it's just fine if you want to say, well, I have, let's see, 4, 5, 6 sigma bonding orbitals. 1, 2, 3, 4, 5, 6. And maybe 4 of them are carbon-hydrogen, 1 of them is carbon-oxygen, 1 of them is carbon-carbon. That's fine. And it's fine if you don't know what the relative energy differences are. I don't know what they are, and I also don't care. You may be uncomfortable not caring about something, and that's okay. I will demonstrate to you why you don't need to care. We can now, while we're here, show you the 6 sigma star orbitals that would come from the corresponding sigma bonding orbitals that are below. Let's see, I've got a pi bond. Now I need to remember a principle. Pi bonds are weaker than sigma bonds because they come from side-by-side overlap, which is worse than end-on-end overlap, and because they hold electrons further away from the nucleus. So that means a pi orbital should be higher in energy than a sigma orbital, and a pi star should be lower in energy than a sigma star. Okay, so I've taken care of these and this. What I'm missing is non-bonding atomic orbitals. Where should those go? Well, they're not bonding, they're not anti-bonding. They should be sort of at our break-even point somewhere in the middle. Now I can fill them up with the available electrons, and I can count how many electrons are in this molecule and fill them up. I'm going to take a shortcut and just say, I know that all the bonding orbitals are filled, and I know I have 2 lone pairs, and then the antibonding orbital should be empty. Now, if you want, you can go and count all the electrons, all the valence electrons there, and convince yourself that we've done this right and we have the correct number of electrons. I also haven't showed opposite spin because I didn't want to draw a little thing on each and every one of those. Those double lines mean an electron pair with opposite spin. So now choice of HOMO and LUMO is easy. The HOMO is the lone pairs on the oxygen, and the LUMO is the pi star. So if this molecule were going to react as a nucleophile, you would predict the most reactive electrons are the lone pairs on that oxygen. That is the case. In 352, when you get to carbonyl chemistry and you have the carbonyl attack an acid to remove its proton. Guess who gets the proton? Lone pairs on the oxygen. In 352, when you have a nucleophile wanting to attack a carbonyl compound, it attacks the pi star. All right? Now, let me tell you a shortcut now that we've gone through this process. Because I know that sigma bonding orbitals are almost never the HOMO, when I'm looking for the highest occupied molecular orbital, I start by looking for lone pairs. Because if they're lone pairs, that's almost always. I realize now that I've said almost always, at least one of you, we got the wheels cranking and thinking, well, what is the exception? And I don't have one. So, okay, basically always, still not good. Always, the lone pair is going to be the HOMO. All right? So I look for that. And if I find it, I'm done. Right? Go ahead.
Is there either lone pair that's more of a HOMO than the other?
Great question. Are they actually equal in energy or are they different? It depends. In some situations, the oxygen behaves as though it were sp2 hybridized, in which case those lone pairs are equal in energy. In other situations, it behaves differently, as though one of the lone pairs is in a p-type orbital and the other is in a more s-rich orbital. Doesn't make any sense, but the answer is not always, but at least one of them will be the HOMO, and I'm never going to ask you.
Okay.
Yeah. Yeah.
And going along with my question, if there were lone pairs on another atom, would that matter as well?
Good question. If there were lone pairs on another atom, would that matter as well? You would, in a case like that, you would be right to be worried about reactions at multiple locations. And in that case, that's all I want you to get. I'm not necessarily worried that you know which is the highest of the highest orbitals, but that you can recognize reactive spots in a molecule. So here is an amino acid. You've got lone pairs on the oxygen, you've got lone pairs on the nitrogen, you've got lone pairs on that oxygen too. Using principles we will learn in Chapter 2, acids and bases, we'll be able to tell which lone pairs are actually higher in energy. But it would be enough at this stage to recognize you got 3 potential spots where you got lone pairs that could react. A preview is that lone pairs on more electronegative atoms are lower in energy. So you'd predict the most reactive electrons there would be on the nitrogen. After Chapter 2, you would predict that. Right now, probably not, which is fine. All right. So look for lone pairs. If there's no lone pairs, look for pi bonds. If there's no pi bonds and no lone pairs, the molecule is probably kind of boring. Now, what about the Lumo? Well, let's go back to that example that I showed you from the slide, BH3, where we learned that the Lumo was an empty p orbital. How did we know that was the case? Well, you have to reason through it this way. First, in BH3, you have 3 boron hydrogen sigma bonds, and so that means you're going to also need 3 boron hydrogen sigma star orbitals. But if you remember the amount of orbitals we mix together, atomic orbitals we mix together, has to equal the number of molecular orbitals that we get out. We have 3 1s orbitals from hydrogen that are contributing, and then for boron, we have a 2s, 2p x, 2py, and 2pz, and we're saying that boron is sp2 hybridized, which accounts for those 3, but we've still, and those sigma bonds, but we still have the p orbital left over. That's one that once you learn that and once you see it once, you probably aren't going to forget it. The other situation where you have an empty p orbital on an atom is where you have, say, a carbocation. And in both of these cases, what clues you to the fact that there's an empty p orbital is that the molecule itself is sp2 hybridized. How do you know it's sp2 hybridized? Because it's only surrounded by 3 things. How do you know it's only surrounded by 3 things? There's no formal charge on that boron. Boron normally comes with 3 valence electrons. It currently owns in this structure 3 valence electrons, so its formal charge should be 0, meaning there can be no hidden lone pair on that boron. And then that leads you to the conclusions that we talked about. Similarly with the carbon, the positive charge on the carbon tells you that carbon only owns 3 electrons, can only be surrounded by 3 things. There's no lone pair, and therefore you've got a p orbital that you haven't accounted for on the carbon. So with all of that in mind, now we know that sigma bonding orbitals are lower in energy than atomic orbitals that we started with. So our p orbital should be right about here, and then the sigma stars would be up there. Fill them up with the available electrons. We've got 6 in this molecule. Oh, the LUMO has to be 2p. So, because that atomic orbital is lower in energy than virtually any of the other antibonding orbitals, if there isn't a p orbital that's empty, that is going to be your LUMO. So look for empty p orbitals first. If not, look for pi bonds, because if there's a pi bond present, as we saw above, the LUMO is most likely going to be the pi star. Okay? Look for lone pairs, look for empty p orbitals, look for pi bonds. And then finally, if it's not going to be a pi star, you look for sigma stars for weak bonds. And right now we've told you about that we've told you just to accept on faith that carbon halide bonds, at least carbon bonds with chlorine or bromine, are relatively weak. So if I were to pick the LUMO of this molecule, that carbon is surrounded by 4 things, so I've accounted for all of the atomic orbitals on carbon. There are 4 sigma bonds and there are 4 sigma stars. That's it. I have to choose one of the sigma stars to be the LUMO, and I'm going to choose the one associated with the weakest bond. Weakest bond, lowest energy sigma star. So the carbon-bromine sigma star is going to be our LUMO. And if you want to know what that looks like, you just have to think about what it would look like to have an orbital, sp3 hybridized orbital on carbon, add to a similar orbital on bromine, in phase versus out of phase. The out of phase combination is what gets you the antibonding orbital. As I move them closer together, they're going to cancel each other out, right? So that means in my orbital, there should be a node, in my sigma star, there should be a node between the 2 atoms. And then in sigma star type orbitals, it actually happens that the large lobe points away from the space between the 2 nuclei. That's a result that comes out of the math. It's difficult, it would be difficult for you to predict. One way of thinking about it is, remember the wave function squared integrated over all space must equal 1. If you cancel out and make the wave function smaller in one area, it's got to get bigger in the other areas to compensate so that the integral stays the same. So this is what the sigma star antibonding orbital looks like. We can draw that superimposed on the structure. And one of the interesting predictions here is that the LUMO of this molecule has a large lobe that is behind the carbon-bromine bond. Now, it's not exactly apparent at this stage, and we'll need to talk about it later, but if you were to have a nucleophile attack this sigma star, it would do so at the carbon from the opposite side, because that's where most of the LUMO is. All right. We need to deal with what happens when a nucleophile attacks an antibonding orbital. Short story is the bond breaks. But we'll need to do that next time. The study guide I've made due tomorrow. I can now make that due Tuesday because we're still a little bit behind. I'm not worried about being behind. I can do whatever I want because I'm the professor, right? But I will always push back the due dates accordingly. You're never going to get penalized because I'm too wordy. All right. Have a good weekend.